Today I will solve the fifth question in electric field chapter, and it's up until now I actually told you that it's two-dimensional problems. First we started with one-dimensional problem and then a two-dimensional problem. But even in that case, the electric field had two components. In that sense, it's two-dimensional, but it still wasn't a two-dimensional charge distribution. So now so what I mean by that is the charge was distributed rather along a one-dimensional, either a curve or a straight line. And this time it will be a little bit different. Now it's a charged disk. So the question is, so let me write it down. So this is the fifth question. So maybe if I draw it, it will be better. So let's take a charge disk with a charge of Q and a radius of R. So it is a disk. So, and the question is, calculate the electric field at a point which is L, so this distance is L, away from the center of the disk. Okay, let's again call this point P. Okay, so how are we going to approach this problem? We are going to use the result that we used in the previous question, which was basically the electric field due to a ring, charged ring, where the distance from the center of the ring and the point P was L. So it's basically similar to this, but of course it was just a one-dimensional problem and we didn't do it. We almost didn't do any integral, right? Here it's a disk. So how are we going to do that? A disk is actually, so this is the idea. This is like the crucial idea, especially in this chapter and also in the next chapter and the following chapters. That's the idea of this, taking a part of an object, an infinitesimal part of an object, and basically constructing the whole object by taking all these infinitesimal parts and building the whole thing. So what I mean by that is we can think disk as rings starting from here and all the way up to R. So you can just take rings infinitely thin, and you can just basically take them and take one ring and put another ring on top of that and on top of that and make a disk, right? So a disk is nothing but a collection of rings which are accumulate one after the other. So, so that's what I meant by using the result of the previous question, which was basically take a ring. We can take this one, for instance. We know what the electric field do to this ring. And let's take the ring's radius to be arbitrary, which is R. And this distance will still be L, and this angle is theta. Right? So let's take this ring. And the radius of this ring is R, but it has some thickness, right? So let's take the thickness of this to be dr. So it's an infinitely thin ring. And what you can do is you can, again, pile up all these rings and make a disk, right? So that's the idea. And let me remind you what the result of the previous question was due to the ring. So electric field of a charged ring, right? That was the result. Was, remember, E was equal to 1 over 4 pi epsilon 0 times the charge of the ring times the distance divided by the L square plus the radius of the ring square with 3/2, right? So this was the result of the previous question, if you remember. And if you don't, please go back to the previous video and check it out. So here, the catch is this ring does not have a finite charge. It's infinitely small, right? So that's why I'm changing this Q to dq. So what we're going to do is we are trying to find out the effect of this infinitely small, charge, which is on this ring, and that's dq. And the effect of that is dE, right? So this is a charged ring where, maybe I should write it here. The charge of this thing is now dq. So the result applies for infinitely small charge as well as finite charge, right? The previous result for the electric field. Okay, now what we can do is We know the effect of that, right? So we basically add all of them up. And remember that this is the magnitude and the direction of that was purely along the x-axis. So I can actually even give a direction for that and make this thing I, right, I hat. So the electric field, which is a collection piling up all these infinitesimal rings, right, dE, that is equal to the electric field E. And this is indeed equal to, since it's only along the x-axis, so that's I hat, the magnitude of dE, of this one, right? And if I take the integral for all rings that make up the ring, make up the disk, right? Make a disk. Okay, so that's the idea. So you take this integral, so you evaluate this integral for all these rings that make a disk. So that's the idea. Okay, so what is this integral again? I'm just going to put this result in here. dqL divided by 4 pi epsilon 0 times L squared plus R squared with 3/2, right? So for all these rings, remember that the middle point of the ring and point P is always L, right? No matter which ring you take. So that's why L is constant. But the ring's radius changes from 0 to capital R, right? So R changes from 0 to capital R. Since R changes from 0 to capital R, so you see the circumference of this ring changes with R because it's 2 pi times R, right? So that bit gets bigger when you take a smaller ring and a bigger ring. And that's why dq is not constant. Changes with R, right, with radius R. So that is not constant. So using that, I can take L out of the integral and this constant out of the integral. So maybe I should write it here. So that will be I'm taking the constants out. So 4 pi epsilon 0, right? And then I have dq divided by the same factor of L squared plus R squared with 3/2. Okay, now I have to do the integral. The variable of this integral is R, right? But dq is still here, and that changes, and R changes, so I have two things that varies with R, so I have to express everything in terms of R, right? So how do we do that? Again, this is what I told you, right? Until now, we didn't consider two-dimensional charge distribution. This is the first question that we do. Now, you see, this is a disk. It's a thin disk. So that's why the charge of this object depends on the area of the part that we take, right? So that's why this dq, which is, maybe I should even draw that dq here. So what I mean by infinitesimal ring is this. So it's a ring where the inner radius is r and the outer radius is r plus dr. What I mean by that is the thickness of the ring is dr. So it's an infinitely thin ring, okay? So what is the charge of this thing? It's related to the area of the ring, right? So how do we write down dq in terms of the charge density? So since this is two-dimensional thing, it's the two-dimensional charge density, which we call sigma, times the area of this infinitesimal object, which is dA. So it's the area of this ring, where the inner radius is r and the outer radius is r plus dr. You can do two things. You can basically subtract the inner circle from the outer circle. That's one way to do that. And the other way to do is basically cutting this and making it almost like a rectangle and multiplying one side with the other, and that will also give you the area of this infinitesimal ring. Or the third way of doing that, which is much easier, is we know the area of a circle, right? That's pi times r squared. So what is infinitesimal area? dA is d of pi r squared. Pi goes out, so that's pi times d of r squared, which is r squared is 2r dr, so that's 2 pi r dr. Right? So this is equal to dA. Okay. Now I can just use that and put it inside dA, and dq is now equal to sigma times 2 pi r dr. Okay? So the electric field is equal to I hat times L divided by 4 pi epsilon 0. Now the integral. Now dq is sigma times 2 pi r dr. So that's sigma times 2 pi r dr. And this is divided by the L squared plus R squared term in here, right? With 3 halves. Maybe it's a good idea, even at this step, to do some cancellation, some simplification. So this 2 pi cancels with that, and we have 2 here. And here, sigma, if it's a uniform charge distribution, and here it is the case, it's a homogeneous charge distribution, I can take it out of the integral, right? So this becomes, so let me write it here, E becomes I hat sigma times L, that goes out, and divided by 2 epsilon 0, and inside the integral I have r dr divided by the same thing in the denominator, right? Okay, that's good. So now I have to do this integral, and this is again similar to what we did in the previous questions. Remember the geometry here. I have theta here, I have r here and L here, and this is L squared plus R squared with square root, right? So this was the geometry, if you remember. So looking at this geometry, I can see that this r divided by L is equal to tangent theta, and hence r is equal to L times tangent theta, and dr is equal to L of d tangent theta, which was d theta over cosine squared theta. So we already did this multiple times, so that's why I don't want to repeat it again. And another identity that we used in the previous question, remember, was L squared plus R squared. So remember that also. L squared plus R squared becomes L squared plus, instead of R, I replace it with this, which is L squared tangent squared theta, right? And if I take L squared parentheses, this becomes L squared 1 plus tan squared theta, which was L squared divided by cosine squared theta. And hence, L squared plus R squared with 3 house power, I can get rid of the square root by this square. So let me write it here. The electric field would be I hat sigma L divided by 2 times epsilon 0. Now the integral. So you will see that it simplifies a lot, right? I have R in here, which is L times tangent theta. So that's L times tangent theta. And instead of tangent theta, I'm going to replace that by sine theta divided by cosine theta. And you will see why I'm doing that. And dr is equal to L d theta divided by cosine squared theta. L d theta divided by cosine squared theta. All of them are divided to this factor in the denominator, which is this 3 house power of this object, which is L squared divided by cosine squared theta with 3 house. So you see that this 1 half factor cancels these two, and this is exactly what I wanted. And this whole object becomes L cubed divided by cosine cube theta. And this cosine cube canceled these cosine terms in here, and that was the reason why I converted tangent theta to this, so that I can get this cancellation. And then this is L cubed, and you see that L cubed here cancels all the L's here. So I get a perfect cancellation, right? So all of that combined will give me I times sigma divided by 2 epsilon 0. The integral becomes a very simple integral, sine theta d theta, right? And then this gives minus cosine theta, right? Okay, now I can go back to the geometry, right? 90 degrees. What was cosine theta? It's L divided by the L squared plus R squared square root. So this is nothing but, let's write it here, I sigma divided by 2 epsilon 0. I'm going to take the minus out, so this is I hat, the direction, Remember what cosine theta was? It's the adjacent side divided by the hypotenuse, so that's L divided by L squared plus R squared with the square root. And R changes from 0 to capital R so that I get the full disk, right? So now I'm going to take the upper range for R and then subtract the lower one. So that will be minus I hat, the direction, to epsilon 0. This guy is going to give me L squared plus capital R squared. And the lower range will give me R is equal to 0, so that will give me just L divided by square root of L squared, which is nothing but L. So this gives us 1, and this gives us this factor. I'm going to take this minus sign and distribute it inside this. So I'm going to use this, so this is 1, right? So this minus factor is going to go in. So I'm using a different color, right? So that's sigma with I hat divided by 2 epsilon 0. So now this guy becomes plus 1 because minus multiplies on plus 1. And this is going to be minus now, right? Plus capital R squared with the square root. Closed parentheses. Okay, so this is the final result for the electric field. Okay, so this was the first example for a two-dimensional charge distribution. Thank you.